This video is the first one about clustering, which is about grouping data. We will look into what clustering is, what techniques exist, and specifically, we will explore hierarchical clustering, a representative method of clustering. To understand clustering analysis, it's important to grasp the differences from classification. Both classification and clustering analysis are used to divide data into different groups based on their characteristics. However, classification involves using labeled data to separate into multiple groups, a supervised learning method. For instance, in the case of incoming emails, classification entails categorizing them as spam or not spam based on their characteristics. On the other hand, clustering analysis involves dividing data into groups without using labeled data, an unsupervised learning method. Essentially, it analyzes the similarities within input data and divides them into arbitrary groups, not predetermined ones. For example, with a number of consumers using online shopping platforms, we can divide them into different groups based on their data, like search history and purchase records, revealing preferences and buying patterns. By doing this, tailored strategies can be developed for each group, leading to enhanced sales promotion effects. Various methods are employed for such clustering, especially hierarchical clustering. Partitioning methods like k-means and density-based methods like dbScan are widely used. Let's start by understanding the hierarchical clustering method. Hierarchical clustering is a connectivity-based clustering approach. The term hierarchical relates to a structure. In this method, clusters are generated based on hierarchical relationships between data points by generally computing the Euclidean distance. The Euclidean distance measurement method calculates the shortest distance between points. You can think of it like the Pythagorean theorem we learned back in school. For example, in a two-dimensional plane, if we have two different points A and B, we calculate the difference between them, take the sum of squares, and then take the square root. If the coordinates of point A are 1, 1, and the coordinates of point B are 5, 5, we can calculate the distance as the square root of 32. By using the calculated Euclidean distances, we establish the hierarchical relationships between data points, leading to the formation of clusters. This hierarchical clustering method, as described, is primarily used not so much to precisely determine the number of clusters, but rather to understand the structure of the data and how clusters are formed. In hierarchical clustering, clusters are represented using dendrograms. A dendrogram has a tree-like structure that illustrates the hierarchical relationships between all the data points in the system. On the x-axis, you have the objects, while the y-axis represents the distances between clusters. Imagine a scenario where A and B form one cluster, C is another cluster, and D, E, and F form a third cluster, as shown in the diagram below. When considering the red line in the dendrogram, you can observe that A and B are connected, C stands alone, and D, E, and F are linked, consequently forming three clusters. Notably, a lower height on the y-axis indicates greater similarity. In this case, E and F are more similar compared to A and B. A significant advantage of dendrograms is that you don't need to specify the number of clusters beforehand. By examining the results and selecting an appropriate height on the dendrogram's y-axis, you can divide the data into clusters at the desired level. Hierarchical clustering can be divided into two methods: agglomerative clustering and divisive clustering. Agglomerative clustering follows a bottom-up approach, where all data points begin as individual clusters and gradually merge with neighboring clusters. This diagram illustrates the process of hierarchical clustering using an agglomerative approach. It starts with one data point and progressively forms clusters by merging those that are closer in distance. On the other hand, divisive clustering employs a top-down approach, starting with all data points in a single cluster and then dividing them into smaller clusters until there is one cluster for each observation. Now, let's proceed with implementing hierarchical clustering in code. The Jupyter Notebook file is available on GitHub, so you can download it and run it directly. To perform the coding, we will import NumPy, Pandas, and the Matplotlib library for graph plotting. Additionally, for hierarchical clustering, we'll import the agglomerative clustering and dendrogram libraries. Here we'll use a synthetic dataset for clustering practice, generated using the make_blobs function provided by scikit-learn. In this case, n_samples represents the number of data points, and centers represents the number of clusters. By setting n_samples to 500 and centers to 5, we will generate a virtual dataset with 500 data points distributed among 5 clusters. This will result in a total of 500 data points, with 100 points in each cluster. If we print the X and Y data for the first 10 points, you'll see the coordinates along with labels indicating which cluster, 0, 1, 2, 3, or 4, each point belongs to. By using the unique function provided by the NumPy library, we can eliminate duplicate values and display those unique values. In the case of the Y data, it contains 5 unique values, 0, 1, 2, 3, and 4, which correspond to a total of 5 clusters. We've then used a combination of the for loop and NumPy's unique function to visualize this information in a 2-dimensional manner. This enables us to input the values 0, 1, 2, 3, and 4 into C to represent each cluster on the graph. Additionally, we added 1 to the values to create a legend representing the 5 clusters. Assuming that these 5 clusters represent the formed clusters in our original data, we can compare these clusters with the results of our clustering analysis. This practice allows us to assess how well the clustering analysis is performing by comparing it to the originally intended 5-cluster structure. To perform agglomerative clustering, we'll use the Euclidean distance and set an initial distance threshold of 5. Below is the code that graphs the original data and the hierarchical clustering results. When visualizing this in 2D, you can observe that a total of 8 clusters have been formed. Looking at the graph, you'll notice that the gray, brown, and pink areas have formed separate clusters, resulting in a clustering analysis that has become overly detailed compared to the original data. Therefore, it seems necessary to fine-tune these results by adjusting the parameters to achieve a more accurate clustering. Using the linkage and dendrogram commands shown here, you can visualize the hierarchical clustering results as a dendrogram. This tree-like structure allows you to divide clusters by adjusting the y-axis value to your desired level. For instance, setting it to 20 would result in 2 clusters, while 15 would yield 3 clusters. By setting a color_ threshold, you can represent the same clusters with the same color. When the color_ threshold is set to 5, the clusters will be displayed in 8 different colors based on the division at the y-axis value of 5. This aligns with the previous slide where we discussed 8 clusters being identified. Therefore, setting the color_ threshold to 10 would divide the clusters into 5 distinct lines, or in other words, 5 clusters. In the previous slide, we set the distance _ threshold to 5. Now, by adjusting it to 10 and rerunning the clustering analysis, we can observe that 5 clusters are formed. In other words, by utilizing the dendrogram, you can comprehend the overall structure and choose an appropriate y-axis value to divide the clusters at the desired level.